Good morning, everybody. Sorry, I'm a bit late today. Uh, yeah, good morning.
Morning.
So, all of you could you please just turn on your video for a few seconds? Okay, Shagnik. Okay. Okay, thank you. Let's begin. So, in the last class, I think we had already arrived at this expression for the rate of ion production following Chapman theory, and we found that that rate of electron or ion production is it has an exponential dependence on height. Where is the height? Height is through this reduced height z parameter, which is expressed as the difference of the instantaneous height from a reference one divided by the scale height of that particular species. So this is where height comes into the picture, and also the angle, the solar zenith angle, that is the angle at which the solar incident radiation is incident on a particular layer. And before that we had and I think we had also derived this relation, right? The electron density profile.
Yes, sir.
Yeah. So that was the original objective, that is to have an idea about how the electron or ionization density varies as a function of height. And in arriving at this kind of a relation, it is a little bit more involved exponential relation, not a simple e to the power something, e to the power minus something, but a little bit more involved. And in arriving at this relation, we had made some simplistic assumptions. Okay, that is, we have assumed that the electrons which are produced by photoionization, they are lost by recombination with their positive counterparts. So that's the only process which is taking place. Although the transport of electrons is also a factor that one takes into account when we go for a more detailed analysis. Okay. And I think I gave that analogy with the situation that if you have, say, for example, in one corner of the room, you have a heap of dust and the wind blows, or you turn on the fan, then that heap of dust gets distributed over a sizable part of the room. So, in case of electrons also, or ions, there is a trans-hemispheric wind. Okay, এই উইন্ডটা কিন্তু not the winds that we experience at the ground level. Like this morning, we had some kind of a strong wind and some lightning and thunderstorms kind of thing. So that is kind of local phenomena limited to within a few kilometers from the surface of the Earth. But these winds in the ionized part of the atmosphere, they are at altitudes of at least say 60 to 100 kilometer above the surface of the Earth, and they blow from one hemisphere to the other during half of the year, and for the other half they blow in the opposite direction. So that also helps in redistribution of the ionization at different heights. So that is the factor which one also takes into account when one goes for a detailed analysis. But for our purpose, I think we could start understanding with this kind of a expression where the exponential variation with height, which we had shown in some of the earlier classes, that kind of an exponential increase followed by a break, then again an exponential increase, and so on. So that kind of a variability could be explained by this kind of an exponential relation. Then this solar zenith angle dependence, that also kind of influences the electron density. Like in the last class, while deriving this expression, we had arrived at this relation that this q chi is something like this, okay, and q at a particular angle x, say for example, and if we just put that to use, say at an arbitrary angle chi, your q chi will be q infinity, which is the photon flux outside the atmosphere times cos of the solar zenith angle divided by the scale height multiplied by the exponential e. So for the overhead condition, this chi will be 0. So chi overhead or O will be q infinity by he, because if you put 0 over here, this will be 1. So we could write that q chi is nothing but q overhead, because this q infinity by he, that is your q overhead times cos chi. And then just to arrive at this expression, where we had shown, where we had understood that this electron density is related to the square root of q by alpha, this ratio. So if we take a square root of on both sides and divide by alpha, then basically we get square root of q chi by alpha is square root of q overhead by alpha cos to the power half chi, because we are doing a square root on both sides, so cos will also be cos to the power half chi. So this is the kind of expression for your peak electron density, and this is the peak electron density for the overhead sun at a particular solar zenith angle of chi. On AJNEOM, which is the electron density for the overhead condition, its peak value or maximum value, that is a function of chi. That means at different angles of solar zenith incident solar zenith angle, this value of the peak electron density, that will be different. So that's a second important deduction that we can have. Okay, now moving ahead, if we consider now the movement of these electrons, there is one more derivation that we can also do from Chapman theory, that from geometry we know that when chi is small, so sec chi is very nearly equal to 1, and also near the peak of peak electron density or peak height of a particular species, at that height near the peak, this z will be small. Okay, so under these conditions, if we go back to this expression for ne, which is ne overhead exponential half 1 minus z minus sec chi e to the power minus z. So we could write this as ne overhead exponential half, because sec chi is very nearly equal to 1. So this will be just 1 minus z minus e to the power minus z exponential half. And if we expand this particular e to the power minus z, this will be like, and limit it up to the quadratic term. So this will be like 1 minus z plus z squared by 2. So these things cancel out, and you are left with this ne overhead e to the power minus z squared by 2, and there's a half in front, so e to the power minus z squared by 4. So this becomes very nearly equal to ne overhead 1 minus z squared by 4 if we limit it to the first order term. So this is a kind of parabolic distribution. So we could say that for a particular Chapman layer, that means whether it is the D layer, the E layer, F1 or F2, for nearly overhead sun, this has got a parabolic shape near the peak. Okay, that means all these kind of breaks that we had observed, if we focus and highlight on any one of these layers near the peak, then we will observe, that means if we calculate what will be the electron densities at those heights near the peak for a particular layer and plot it, then we will observe that it is more like a parabolic distribution around that peak of the particular layer. Now, the next thing which is important for us to understand is that these electrons or ions, they are essentially immersed in an electric field as well as a magnetic field. That means because of the presence of these electrons or ions, there is some kind of a electric field which is present, and that electric field, in that electric field, if you have an electron or an ion moving, then the situation becomes interesting, and you have some examples which we will quickly go through. So what happens is that if we express that electric field simply as one of the simplest sinusoidal form, that means the electric field which is present in the ionized part of the atmosphere through which the electrons or ions are moving, if we express that as some kind of a simple E naught sine omega t, then we could write the equation of motion as something like this. That is your m dv dt, that will be simply the charge times the electric field. This is well known to us. That means when charges move in an electric field, then this is the kind of distribution, this is the kind of equation that is there. So if we now integrate both sides, we get essentially this V will be small e into E0. Small e is the electron charge. Okay, remember. Just be careful. That means in Chapman theory and also in some of the earlier derivations, the small e was mostly the exponentially. But here, because we are considering the motion of electrons in an fluctuating electric field, so this small e is actually the electron charge. So if we integrate this relation, we get this V is integral of small e E0 by m sine omega t. Okay, sorry, there will be a dt over here, and I missed out that dt. And so if you perform this integration, it will be like minus e into E0 by m omega cos omega t. If you integrate this will be like there will be a omega in the denominator and cos omega t. Now, if we try to estimate the conduction current which is associated with this movement with this medium, with this situation where you have electrons moving in a fluctuating electric field, then that conduction current, if I refer to that as IC, say for example, then that IC will be nothing but the product of the electron density, sorry, the electron charge times the velocity of the electrons. So if you just put the value of V over here in this expression, then this becomes something like minus NE. This E and that E becomes E squared by M omega into E naught cos omega t. So this is the expression for the conduction current. Okay. And the displacement current, if I refer to that as ID, we know that a displacement current essentially arises due to this fluctuating electric field. So that could be represented by K upon 4 pi dE dt. This K is the dielectric constant of the medium. And if you perform the differentiation of this electric field with respect to time, then you get this as K, that means this electric field, this term, then you get K E naught by 4 pi omega cos of omega t. Okay. So this is the conduction and that's the displacement current. So the total current in the medium, that will be given by K minus 4 pi Ne into E square by 4 omega square. That means we are taking this E naught by 4 pi omega cos omega t outside the bracket, this E naught by 4 pi omega cos of omega t. This entire term, product of these terms, we are taking outside the bracket. So within the bracket, we get K minus this term multiplied by 4 pi and these things. So it becomes K minus 4 pi Ne into E square by M omega square. So if we just compare this expression, this particular expression with the standard expression, what we arrive is that is very interesting, that as if the dielectric constant of the medium, this has decreased from a value of K to K minus 4 pi Ne into E square by M omega square, simply because we are dealing with a situation where we have electrons moving through a medium which contains an electric field, a fluctuating electric field. That means the effect of these electrons or ionization as well as this fluctuating electric field is to reduce the dielectric constant from a value of K. Okay, over here, as you can see, from K it decreases to K minus 4 pi Ne into E square by M omega square. Okay. So for free space, the dielectric constant of air we know, or for free space, is 1. So this effective dielectric constant that as given in this term within the bracket, that becomes something like 1 minus 4 pi Ne into E square by M omega square. Now, just like an optical medium where, we had earlier learnt about the refractive indices in earlier classes, and similarly, in an ionized medium also, you have the radio refractive index. This is not optical, but radio. And this is a common property for, all electromagnetic waves propagating through medium. I mean, whatever properties are satisfied by optical waves or optical signals, almost all of them are, kind of satisfied by the radio waves as well. So this mu radio, I mean, I have put this subscript radio just to distinguish it from the optical situation. So this mu radio is square root of this dielectric constant. So it will be square root of this 1 minus 4 pi Ne into E square by m omega square. Now, pay attention, very good, very clear attention to this fact that when a signal is transmitted from the surface of the earth, okay, upwards at any angle, then up to the peak height or up to the height of maximum ionization, the common understanding that we have now is that this electron or ion density increases with height. Taito? That up to about 350 or 400 kilometer, the electron density that increases with height in an exponential manner or whatever, and above that peak height of maximum ionization, above that height, it decreases. Okay, so that means that as a function of height, this Ne increases up to say 350 or 400 kilometer. So this second term within the square root sign, that also increases. So this whole term under the square root, that decreases. So that means as a function of height, mu radio, that also decreases. Do you get the point? That means starting from the transmission of a radio signal from ground upwards, up to the height of maximum ionization, the value of this Ne increases with height. So the value of this second term increases with height. So this entire term within the square root, that decreases with height. So that means mu radio decreases with height. That means just like we used to say in optics, that the signal is passing from a denser to a rarer or rarer to a denser medium. So here also we could say that the radio signal is progressively passing from one layer which is having a higher value of mu radio to the next higher layer which is having a lower value of mu radio, because with height, up to the height of maximum ionization, this radio refractive index, that is decreasing with height. Okay, this is something which is very fundamental to understand, because this is the principle, this is the understanding, and this is the scheme following which radio waves get reflected from a particular ionized layer, and this is the principle following which long distance radio wave propagation could be, or radio wave communication could be achieved. Of course, we do not take into consideration here the cases of satellite based radio communication, but we are considering the case of long distance radio wave propagation using the ionized part of the atmosphere or ionized layers as some kind of a reflector of radio signals. So once the mu radio refractive index, that means the radio refractive index has been defined in this situation, the corresponding phase velocity will be simply this c upon mu, and the group velocity is given by this mu into c. These are some things which we already know, which you already know perhaps from your classes on electromagnetic fields and waves in the third semester. So the group velocity will be given by simply c into this mu radio, that means square root of 1 minus 4 pi Ne into E square by m omega square. So in this expression, I think all of you could understand that E is the electron charge, m is the mass, and omega equal to 2 pi f. That is the frequency. F is the frequency of transmission. So the group velocity is given by an expression something like this. So once again, if we apply our already acquired knowledge that up to the height of maximum ionization, the electron density that increases with height, up to the height of say 350 to 400 kilometer, the electron density increases with height. So once again, this term within the second term within the square root sign, that becomes larger with height up to the peak height. So this entire term becomes smaller. So the group velocity also becomes smaller. So practically speaking, this is actually leading us to the condition for reflection of radio waves. The group velocity will decrease as the signal goes higher and higher up to the height of maximum ionization, of course. And there will be a limiting stage, a limiting condition when this group velocity will become zero, and it is at that height, under that condition, that the radio wave will be completely reflected back, or it will turn back. Okay, so we are gradually heading in the direction of understanding what is the requirement for reflection of a radio wave from the ionized layer. This kind of a mathematical formulation is extremely necessary for radio engineers like you, because you cannot leave it to chance. Your company asks you to set up a radio communication link between, say, Kolkata and Boston. Then you cannot leave it to chance that let us transmit a signal and see if it gets reflected or not. You have to have a foolproof model, a foolproof calculation that, yes, this is the frequency at which we should transmit. The angle will also come into the picture. We will come to it later on, at what angle you will transmit. And this signal will suffer a reflection and will be reflected and will be received by the destination receiver. So, if we once again apply the very well-known Snell's law for this condition, so we can say that suppose if a particular radio signal is incident from air, that means from a neutral medium, say, on the ionized atmosphere, then we could write this condition as 1 into sine I is mu into sine R. And in the limiting case of reflection, that means the total internal reflection, this will be, this angle of refraction will be 90 degree. So your sine I will be equal to mu, and under that condition this sine I will be simply equals to mu, because if you put r equal to 90, this will be 1. So your sine I will be square root of 1 minus 4 pi ne into e square by m omega square. Further, if this signal is incident vertically, then this angle of incidence will also be equal to 0. So under that special condition, we are trying to reach the condition of reflection of this radio signal at vertical incidence. So this will be kind of 4 pi ne into e square by m omega square equals to 1, where your omega is 2 pi f, and from there you can get this condition that ne equals to m pi f square by e square. Okay, simply just put omega equals to 2 pi f, so omega square will be 4 pi square f square. So this this 4 will cancel out, 1 pi will cancel out, and you will have this relation that ne is equal to m pi into f square by e square. Now, I will just ask you to put the values of E, M, and pi. Of course, 3.14 something. So put the values of E and M in the electrostatic unit, in the ECU unit, and see if you are getting this particular relation or not. Okay, just work it out for me. That put the values of E and M in electrostatic unit, and then you see whether you are getting this particular relation or not. Just do it and let me know.
Yes, sir, করেছি।
হ্যালো, বলো।
স্যার এসছে এরকমই 1.09 এরকম
আচ্ছা,
আছে।
সমনা, তাহলে যেটা একটা কাজ করো, আমি স্টপ করছি প্রেজেন্টিং। তুমি জাস্ট তোমার খাতায় যেটা করেছো সেটা একটু আমাদের দেখাও। ওকে, that how you have done it. যেটা খাতায় করেছো সেটা আমাদের একটু তোমার একটু দেখাও। হ্যাঁ, আরেকটু এ করো, এনলার্জ করো। ওকে, সো একটু বলে দাও আমাদের কোনটা কি ভ্যালু।
এম আর ই এর ভ্যালুটা পুট করেছি।
হ্যাঁ, মানে 10 টু দি পাওয়ার মাইনাস, এটা কি 10 টু দি পাওয়ার 9.1 ইন্টু 10 টু দি পাওয়ার মাইনাস 28 হবে না 31 হবে?
31।
হ্যালো।
Yes, sir.
So with this value in the numerator, will that be 9.1 10 to the power minus 31 or 28?
Yes, sir, 28 CGS এ 28 হবে।
But we are using this EFU, okay, electrostatic unit. But this result is like 1.09. this result is 1.09. It should be like 1.24 around that. এটা একবার check করো if there is any error in the calculation. Yes, somebody said something now. মানে তোমার 1.09 আসছে না বা 1.24 আসছে না নাকি? না, সেটা কিছু একটা তাহলে তোমার দেখো প্রবলেম হচ্ছে হয়তো, মানে ইলেকট্রোস্ট্যাটিক ইউনিটে ইয়েস চিরন্তন
স্যার এটাকে ইন টার্মস অফ মেগাহার্টজ ফ্রিকোয়েন্সিটা ইন টার্মস অফ মেগাহার্টজ এ করতে হবে, তো তাহলে তো ডিভাইড বাই 10⁻12 মতো করতে হবে আনার জন্য নাকি?
So could you show me, Chirantan, what you have done?
Sir, I have just used a calculator to do it, so I'll do it formally and then wait for you. Just a minute.
Okay. Anyway, I think all of you just do this. It will be something like this 1.24 into 10 to the power 4 only. And yeah, so it will be like 1.24 into 10 to the power 4 f square. So now if we just try to have some idea about what is meant by this f over here, okay, so what we can say is that this is the highest frequency which will be reflected back at vertical incidence. This f, f derived from this relation has got a special name, which is critical frequency. And sometimes, almost equal in value, exactly equal in value is the plasma frequency, which is associated with that. So this critical frequency is nothing but the highest value of the plasma frequency at vertical incidence. The plasma frequency is dependent on this NE. So at different values of NE, this plasma frequency will have different values. And for vertical incidence, the highest value which is received, that is the critical frequency. That means the idea is that now naturally the question comes to the mind that how do we implement this? See, the situation is that you have a radio transmitter, and in that radio transmitter you have a variable frequency option. That does not mean an unlimited variable frequency. Usually these kind of transmitters, they allow your vertically transmitted signal to have frequency ranges starting from say 1 megahertz to about 50 megahertz. Okay, so just in order to have an idea that what could be the typical values of this f, okay, can I ask you to do one very simple calculation? That is, we now know the maximum values of electron or ionization density for the different layers, okay, that is for the D layer, it is like, for the D layer, it is like 10 to the power 5 per cc, okay, and then for the E layer, sorry, for the D layer, I think it is 10 to the power 4, not 5, 10 to the power 4. For the E layer, this is 10 to the power 5 per cc. Then for the F1 layer, this is like 10 to the power 6 per cc. And for the F2 layer, it is suppose 5 into 10 to the power 6 per cc. So could you please calculate, the corresponding values of F or FC, so to say, for each of these layers? Could you please tell me the corresponding values? Because that will give you an idea that what are the kind of frequencies that we are typically talking about. Okay, একটু ক্যালকুলেশনটা করে আমাকে একটু ভ্যালুগুলো বলো তো, assuming these values of electron and electron density. Just put that in that expression, 1.24 into 10 to the power 4 f square. বলো। আচ্ছা, তোমার নাম কি বলো তো একটু, আমি তো এখানে দেখতে পাচ্ছি না, বলো। ওকে, মানে 1.24 ওটা এসছে। Okay, fine. So the next step is that you put the values of n for each of these different layers, the peak value, because corresponding to the peak value, you will have the maximum value of this plasma frequency, and that maximum value of plasma frequency is nothing but your critical frequency. So just value গুলো put করে একটু আমাকে বলো কত মেগাহার্টজ আসছে।
তো ফসফেটটা 0.89 মতো আসছে মেগাহার্টজ।
একটু আরেকটু জোরে বলো।
So 0.89.
0.89 for the D layer.
হ্যাঁ স্যার আমি এসছে ভ্যালুটা।
Okay, বাকিটা আমাকে একটু কনফার্ম করো whether you are getting this or not, because I don't have ready-made solutions.
তারপর এটা 2.84 আসছে।
Yes, sir, 0.89 megahertz টা এসছে।
Okay.
তারপর এটা 2.84 মেগাহার্টজ আসবে।
2.84.
ইয়েস স্যার।
Okay.
তারপর এটা 8.9 মেগাহার্টজ।
8.9. Okay.
and লাস্ট এটা 20.08।
I put 20.1. So কি বাকিরা কি একদম চুপচাপ হয়ে গেলে কেন? সায়নী রয়,
স্যার করছি।
ওকে, সম্রাট,
হ্যাঁ স্যার করছি।
ওকে, এই এত সময় লাগছে কেন? এই তো খালি এখানে মানে জাস্ট এন এর ভ্যালুটা পুট করবে, করে ডিভাইড করে বলবে।
হ্যাঁ স্যার আসছে এইগুলো।
কি বলছো বলো এটা?
স্যার সোহম।
ওকে,
হ্যাঁ স্যার এরকমই এসছে।
okay. So I will assume that this is a very simple problem, so all of you will be able to do this. Now, as I was telling you that the situation in case of propagation of these, signals through a medium surrounding Earth is a little bit more tricky than some kind of a simple theoretical situation. Because here, other than the fluctuating electric field, we also have a magnetic field, the geomagnetic field. That means the magnetic field which we attribute to Earth. That means from our very early classes, we had learned that, or we had imagined that there is some kind of a bar magnet located at the center of the Earth, and that bar magnet is essentially, the source of this geomagnetism. Although the phenomena of magnetism, to be very honest, is less well understood compared to that of electricity. ইলেকট্রিসিটি আমরা অনেক ভালোভাবে বুঝি, ইলেকট্রিক ফিল্ড অনেক ভালোভাবে বুঝি, কিন্তু ম্যাগনেটিজম বা ম্যাগনেটিক ফিল্ড কিন্তু আমরা এখনো পর্যন্ত we do not understand that very well. Okay, I mean as well as electric field or electricity. So one of the main reasons behind that could be the fact that we have gone millions of kilometers in space, but within the surface of the Earth, we have hardly gone beyond a few kilometers. Okay, so if you assume that the source of some kind of an electric field is within a particular object, then an in situ observation or in situ measurement. This in situ term means that you are making the measurement there itself. যেখানে হচ্ছে সেখানে গিয়ে আমি মেজারমেন্ট করছি। সো দ্যাট অপশন ইজ নট দেয়ার for this magnetic field. We could measure, the horizontal intensity and other things, but not explore in too much details the source of that. Okay. So keeping that in mind, another aspect which is also important is that this magnetic field, the geomagnetic field, we know that it originates, its manifestation on magnetic material is something like this. I think all of you have done this experiment in your high secondary classes, that you sprinkle some magnetic material around the bar magnet and find some kind of a concentric circles originating from one end of the bar magnet and terminating at the other. Now, there we had also seen that that bar magnet has got the property of magnetism or magnetic field. It exerts a magnetic field, but that magnetic field does not fluctuate. Does not fluctuate over periods of time with which we are concerned. The Earth's magnetic field does flip, but that happens over a period of millions of years. The last time Earth's magnetic field flipped was when the dinosaurs became extinct. Okay, so it is of that periodicity. So for all practical purposes, we could assume that the magnetic field is nearly constant. So we have a situation which we are dealing in parts. First, we assume that the electric field is fluctuating. We dealt with the situation that under the influence of that kind of a fluctuating electric field, the electrons or ions are moving following a certain pattern, and we derived the condition for reflection from an ionized atmosphere. And now we will deal with the propagation in the presence of a magnetic field which is kind of constant. Okay. So when that kind of a situation happens, eventually the final practical situation is that you have to merge the two situations together. Then only you will be able to arrive at some kind of a realistic situation. Okay. So far, we are just dealing them as independent entities in this whole situation, having the having the electric field which is fluctuating and the magnetic field which is more or less constant. So I think in the next class we will continue with this discussion about the propagation in the presence of a constant magnetic field. Now let me have your attendance. So today is 4th May. Okay, Shubhodip Mukherjee.
Yes, sir.
Mousumi Shah. Srija Chakraborty. Okay. Ramona Mojumdar.
Present, sir.
Mousumi Mondol.
Yes, sir.
Samrat Malakar.
Present, sir.
Debraj Das. Debraj. Soumajit Bosak. দেবাঙ্গনা বসাক,
Present, sir.
অরূপ কুমার মারিক,
Yes, sir.
সায়নী রয়,
প্রেজেন্ট স্যার।
সোহম পল,
প্রেজেন্ট স্যার।
সাগ্নিক নায়েক,
Present, sir.
চিরন্তন গাঙ্গুলি,
প্রেজেন্ট স্যার।
অনিরুদ্ধ মণ্ডল,
Present, sir.
অমিত্রাক্ষর সান্যাল,
প্রেজেন্ট স্যার।
পথিকৃৎ গুপ্তা, is Pothikrit okay? I mean, is he attending other classes? Any of you know whether Pothikrit is attending other classes or not?
Yes, sir.
Okay. Shreyosri Roy,
Present, sir.
Ritik Majumdar,
Yes, sir.
Ritik, what happened to you?
Yes, sir.
What happened to you? I mean, you were absent in the last 3 classes, I think.
Sir, I was having some emergency.
Okay. Suprabhat Mukherjee, Bhattacharjee,
প্রেজেন্ট স্যার।
Shayan Datto.
Hello, sir. Sir.
Shayan Datto present?
স্যার স্যার আমি দেবরাজ মানে মাইটার একটু প্রবলেম করছিল।
Okay. Okay. Okay, so thank you.
থ্যাংক ইউ স্যার।